Welcome to the Explainer. Today we're jumping straight into the mechanics of simple chemical reactions, specifically focusing entirely on complete Lesson 8.1 from our source material. So let's get right into it.
To get us started, think about a spectacularly bursting firework, a puddle of melting ice, and a glowing piece of burning coal. What do they all have in common? Well, they all represent a profound change to materials. But not all changes are created equal. Some just alter how things look on the surface, while others literally rewrite the entire identity of the substance itself.
Section 1. Physical versus chemical properties.
So, we really need to break down the difference between physical properties and chemical properties. You can think of physical properties as the basic surface-level facts of a substance. Like, what color is it? Is it a solid, a liquid, or a gas? Take iron, for instance. It's a heavy gray solid with a massive melting point of 1538 degrees Celsius. But its chemical properties, that's where the hidden potential lies. It's all about how a substance behaves when it actually meets another substance, like how iron uniquely combines with sulfur.
Section 2. Spotting chemical changes.
What's really fascinating is that chemical reactions aren't just locked away in fancy science labs with folks wearing white coats. They're happening constantly, everywhere around us. When plants grow, that's a chemical reaction. When wood decays in a forest, yep, chemical reaction. In fact, there are incredibly complex reactions happening inside you right this very second as your body digests your last meal.
To really understand this, we have to look at the microscopic level during a change. Imagine we have an iron atom and a sulfur atom. When they get heated up together, they don't just sit next to each other, they bond. They physically lock together to form a completely brand new compound, iron sulfide. The original, individual materials, they're totally gone.
And this brings us to the crucial terminology we use to describe this transformation. The reactants are your starting ingredients. They're the substances that react together in the first place, like our iron and sulfur. And the product is exactly what it sounds like. It's the brand new substance produced by the reaction, which in our little example was the iron sulfide.
Section 3. Trial by fire.
Burning is actually a classic textbook chemical reaction. When you see charcoal burning on a grill, you aren't just seeing heat. You're witnessing the element carbon aggressively reacting with the oxygen in the air around it. Those reactants, the carbon and the oxygen, bond to create entirely new products. You get carbon dioxide gas, which just floats away, and the solid ashes left behind.
But honestly, charcoal is pretty tame compared to something like magnesium. Take a mundane, shiny, solid strip of magnesium ribbon. Seems pretty normal, right? But apply a flame to it, and it reacts with the oxygen in the air, burning with this blindingly bright white light. It is so incredibly intense that laboratory safety guidelines literally tell you not to look directly at it.
This really highlights just how total this transformation is. Think about it. We started with magnesium, a shiny metal that conducts electricity, and oxygen, an invisible, odorless gas. But the product? Magnesium oxide. It's a solid, white, powdery compound that absolutely does not conduct electricity. The properties have completely flipped. The reactants fundamentally change their entire identity to become the product.
Section 4. Water and acid reactions. Now let's talk about potassium. It's a highly unusual metal. Physically, it is so soft you can slice it with a normal kitchen knife, but chemically, it is wildly reactive. If you place just a small piece of this soft metal into a trough of water, it instantly gives off hydrogen gas. And the reaction produces so much intense heat in a fraction of a second that the hydrogen gas actually ignites into flames right there in the water. It's just wild.
Because these reactions are so intensely violent and unpredictable, strict laboratory safety protocols are absolutely non-negotiable here. Reactions like potassium and water are strictly for teacher demonstrations only. Everyone in the room has to wear safety glasses, and a heavy-duty safety screen has to be placed in front of the beaker to protect observers from any volatile splashing or sudden sparks. Science is fascinating for sure, but safety always comes first.
Section 5. The hydrogen pop test. So we just talked about hydrogen gas being produced, but gas is usually completely invisible. How can scientists actually prove what kind of mystery gas is bubbling up out of these reactions? Well, to answer that, we look at a different setup. Imagine a piece of solid magnesium dropped into a test tube of liquid hydrochloric acid. Immediately, a vigorous reaction kicks off. The products forming are magnesium chloride and a very steady, very rapid stream of invisible gas bubbles rising to the top. We highly suspect it's hydrogen, but we need to prove it.
To prove it, we run a very careful step-by-step diagnostic process. First, we light a small wooden splint. Second, and this is the absolutely crucial part, the experimenter has to keep their finger tightly sealed over the top of the bubbling test tube. Why? Because hydrogen gas is significantly lighter than air. If you don't physically trap it, it just floats away. Finally, you quickly remove your finger and place the lit splint right into the mouth of the test tube.
And here is the really exciting payoff. When the open flame meets that trapped hydrogen gas, you hear this very distinct, iconic, squeaky pop sound. That pop, it's actually a miniature secondary chemical reaction happening right there in the tube. The hydrogen gas is violently reacting with the oxygen in the room's air to form water. If you get that pop, you have absolutely proven the presence of hydrogen.
So we've seen metals burn bright white, soft elements literally explode in water, and invisible gases announce themselves with a squeaky pop. All of these are undeniable chemical reactions, where old materials become totally new substances. But this leaves us with a truly profound question to ponder. Once a completely new substance is formed, like that white powdery magnesium oxide, can we ever reverse the process? Can we unmix the ingredients, break the chemical bonds, and somehow get our original shiny metal and invisible oxygen back? Keep that in mind as you continue your journey into the incredible rules of chemistry. Thanks so much for joining me for this explainer.